During 1964, Los Alamos scientific laboratory effort on the Rover program continued both at Los Alamos and at the Nuclear Rocket Development Station in Nevada. At Los Alamos, the work was concentrated on developing and manufacturing improved fuel elements, perfecting better instrumentation techniques, and designing advanced reactor systems for the Phoebus phase of the Rover program. At NRDS, 4 major tests were conducted: the Kiwi B4D cold flow machine, 2 highly successful hot run reactors, the B4D202 and B4E301, and the rather spectacular Kiwi transient nuclear test, or the Kiwi TNT. The B4D cold flow machine was tested at Test Cell C in mid-February of 1964. Like its predecessor, the B4B cold flow tested in August 1963, the B4D incorporated core support changes which corrected vibration problems that occurred in earlier Kiwi B reactors. Except for minor design changes in the core periphery and inlet and outlet regions of the B4D, it was identical with the earlier B4B cold flow. The primary objectives for the B4D cold flow were to verify the dynamic stability and structural integrity of the new design and to investigate early transient behavior of a reactor start on liquid hydrogen. A total of 4 cold flow tests were conducted. One was made with flow induced by 80 pounds per square inch of Dewar pressure, followed by liquid hydrogen startup profiles corresponding to reactor gas temperature ramps of 0 degrees, 40 degrees, and 100 degrees Fahrenheit per second. The cryogenic starts were successful, with no difficulties being encountered. Throughout the tests, all components functioned properly, and all objectives were accomplished. The test of the B4D cold flow marked the first use of a new turbine-driven pump to move liquid hydrogen from the storage dewars to the reactor. The turbine, which replaced an electric drive system, was operated at speeds up to 28,000 revolutions per minute to deliver approximately 87 pounds of liquid hydrogen per second. Concurrent with the cold flow tests at Test Cell C, the assembly of the Kiwi B4D202 reactor was underway at the MAD building. This would be the first hot reactor tested since the B4A, 13 months earlier, when serious vibration problems occurred. The new B4D202 was basically the same as the B4A, except that it incorporated the core support changes proved in the cold flow tests. 2 types of fuel elements were used in this reactor. The majority of the elements were loaded with uranium oxide. There were 212 experimental elements made of pyrocarbon-coated uranium carbide beads. The hot run of the Kiwi B4D202 at Test Cell C was scheduled for April 13, 1964. The principal aim of the hot test was to operate the reactor at design conditions. The plan called for 2 holds, one at 2,500 degrees Rankine, a flow rate of 25 pounds of liquid hydrogen per second, at a power level of 213 megawatts. The other at 3,200 degrees Rankine, a flow rate of 70 pounds per second liquid hydrogen, and a power level of 784 megawatts. If the supply of liquid hydrogen permitted, a full power hold of 8 minutes was planned for the run.
Stabilize, switch to run.
Right.
MTO at the end of the second ramp, switch to hold.
Right. We're holding 2,500, station 26, increasing now.
The test was terminated after about 1 minute of the nominal full power hold because of a hydrogen fire at the nozzle. The fire resulted when a small explosion, or explosions, ruptured 8 cooling tubes in the nozzle and allowed hydrogen to leak to the outside. The cause of the damage is believed to be the presence of liquid air in the interstices between the nozzle coolant tubes and the pressure shelf. In spite of the fire and premature termination of the run, all major objectives of the test were achieved. The condition of the core after the run was near perfect. There were no cracked or broken fuel elements, and only minor corrosion was found in unprotected areas. At Los Alamos, work continued on the development of improved fuel element materials and methods for applying niobium carbide protective coatings. The experimental bead-loaded elements tested in the 202 core demonstrated improved strength and dimensional stability over the older oxide-loaded elements. The next reactor to be tested, the B4E301, would be made entirely of the bead-loaded elements. An experimental beaded element was developed which has a glued-on hot-end tip of unloaded graphite. The niobium carbide coating forms a stronger bond with the unloaded graphite and should provide improved resistance to chipping and corrosion. 17 of these experimental elements were tested in the 301 core. The B4E301 reactor was moved to Test Cell C in late July 1964. Except for the different type fuel elements, it was identical with the B4D202. Since the 301 nozzle was similar to the one that failed during the 202 run, a helium-purged shroud around the base of the nozzle was added to prevent liquid air from entering the nozzle in this area. The full power run of the B4E301 was conducted August 28, 1964. The major objective of the test was to run the reactor just below full power for as long as the liquid hydrogen storage capacity would allow. The reactor operated smoothly throughout the run with none of the problems that plagued earlier runs. Maximum fuel element temperatures of 4,300 degrees Rankine were achieved with a maximum calculated thermal power of about 937 megawatts. The full power hold was halted after 8 minutes when the supply of liquid hydrogen had been depleted. Because the run was so smooth, it was decided to replenish the liquid hydrogen supply and restart the reactor. The restart was run September 10, 1964, 13 days after the first run. The major objectives for the restart were to confirm the recycling capability of the reactor and to perform a control system dynamics check. The reactor and all systems again performed perfectly. It was shut down after operating for 2½ minutes near full power. Disassembly and inspection of the core and clusters revealed that out of 1,542 core elements, only 14 were broken or had corroded through. 11 of these were irregular peripheral elements. In spite of this localized damage, the general condition of the core was excellent, and the reactor could safely have been run longer or recycled again. The B4E301 was the final reactor in the Kiwi series. Phoebus would be the next series in the Rover program. Fuel elements for the first Phoebus reactor, the 1A, were being fabricated in Los Alamos in the latter part of 1964. The 1A fuel elements would be very similar to those of the Kiwi B reactors, except that all fuel elements would be of the beaded fuel, glued tip design. The Phoebus 1A would be tested in Nevada in mid-1965. At Los Alamos, design work was underway on the larger Phoebus 2 reactors, which will have 5 times the power of the Kiwi B and Phoebus 1 designs. The honeycomb assembly was used to evaluate designs for the Phoebus 2. Proposed fuel and graphite loadings were mocked up in the assembly so that realistic neutronic studies could be made. In addition, a zero-power vertical mock-up of the Phoebus 2 core design was assembled for studies. The fuel, graphite, and beryllium reflector components of the proposed design were duplicated in this assembly. In preparation for testing of the larger Phoebus 2 reactors, design work was completed for modifications to the Test Cell C complex. Additions will include 2 500,000-gallon liquid hydrogen dewars, a 250,000-gallon water tank, a heat exchanger, and additional liquid nitrogen storage tanks. The modifications will permit a 1-hour runtime with 1,000 megawatt reactors and a 30-minute runtime with 5,000 megawatt reactors in the Phoebus II class. The major effort of the rover flight safety program during 1964 concerned the Kiwi transient nuclear test, or Kiwi TNT. In this experiment, a Kiwi B reactor was modified so that it could be forced to destroy itself through an extremely rapid excursion. The experiment was conducted to determine the consequences of potential nuclear accidents involving nuclear rockets and to study a possible method of disposing of nuclear rockets after use. The experiment was conducted at a special site located near the Test Cell C complex. Although preparations for the TNT experiment were completed in late December 1964, the test could not be run until January 12, 1965, when weather conditions were satisfactory.
Minus 15. Rocket power off. Minus 10. We have a go on Millikan CEC. 7, 6, 5, 4, 3, 2, 1. Fire. Timer's on.
In spite of the rather spectacular appearance of the Kiwi TNT experiment, the mechanical and radiation effects were limited to a rather small area. General air shock and shrapnel damage was limited to a radius of 100 to 200 feet. Massive biological radiation effects extended to about 600 feet, with a mean lethal dosage distance of about 450 feet. The TNT test was undertaken only after extensive calculations had been made to predict the detailed history of the nuclear excursion. Results indicate that the energy release, rate of reaction, and external effects were all within the limits predicted. There is now a known point of departure for extending such calculations to a variety of situations. The primary application of the results will be to the nuclear safety aspects of nuclear propulsion operations, and to a possible method for disposing of flight systems after operation. The 1965 rover schedule calls for the first Phoebus I reactor hot run in early summer at Test Cell C. Construction of the dewars and other Test Cell C modifications will continue throughout the year. At Los Alamos, work will continue on improving fuel elements and designing the 5,000 megawatt Phoebus II reactors that are scheduled for testing in early 1967.